So I'd like to do some numerical examples in this video of orthogonal projection. In our previous video, we saw that if v1 through vk are pairwise orthogonal, meaning that the dot product of any pair is 0, then the vector w in the span of these vectors that minimizes this quantity is given by this formula. So here, our first example. Which w in the span of the vectors 1, 1, 1 and 1, 0, negative 1 is closest to the vector 6, 6, 0? So this is an example of such a problem we've been discussing. This first vector is maybe the vector v1, this second vector v2, and this is the vector x. I'm lucky in this example because the dot product of v1 and v2 is 0. So they're already orthogonal. So the answer is immediate. I could just use this fact. The vector w is the vector 1, 1, 1 dotted with my vector x, 6, 6, 0, divided by the length of 1, 1, 1 with itself. Okay, the dot product of 1, 1, 1 with itself. All that, this is a constant. All that is going to be times 1, 1, 1. And then I'm going to add the dot product of 1, 0, negative 1 with 6, 6, 0. Divided by the dot product of 1, 0, negative 1 with itself. And that will be times 1, 0, negative 1. Then you could just do the dot product calculations. You could explicitly do the work. Let's see what you get here. So this would be 12 over 3 times the vector 1, 1, 1. Plus, let's see here, the dot product would be 6 over 2. So 6 over 2 times the vector 1, 0, negative 1. So that would be 4 plus 3. I guess I get 7. And 4 plus 0, 4. And 4 minus 3, which is 1. Okay. Let's do another example. This time, watch this. So which vector in the span of 1, 0, 0 and 1, 1, 0 is closest to the vector 1, 3, 1? So it's a similar looking problem. However, this time I'm not so lucky, because the two vectors that I have are not pairwise orthogonal. If I take the dot product of these two vectors, I don't get 0. Let me draw the situation in R3. So I have vectors in R3. So let me have an x, y, and a z axis. So here's x coming out of the page, y to the right, and z up this way. The vector 1, 0, 0 is maybe this red vector here. The vector 1, 1, 0 is a vector that's 1 unit in the x direction and 1 unit in the y direction. So the vector 1, 1, 0 could be the second red vector. The span of these two vectors is all possible linear combinations of them. Any combination of these two vectors will have third component 0. So you might be able to see that the span of these two vectors describes the xy plane. So the xy plane is the span of my vectors. Let's say that's v1 and that's v2. I cannot use this fact right off the bat, however, because they're not pairwise orthogonal. However, I could still describe the same span by changing v2. So here's my answer. Consider the span of not my original vectors, but instead 1, 0, 0 and 0, 1, 0. So I'm going to keep this first red vector the same, but I'm going to move this second vector. I'm going to rotate it over so that it's parallel to the y-axis. That way, my two vectors are orthogonal, but they still describe the same span. They still describe the xy plane. I've just chosen different basis vectors, different vectors to represent that span. And I chose them in such a way so that their dot product is 0. Now, and only now, can I employ this fact up here. So the answer is, oops, I already wrote answer. So that means the vector W I'm looking for is equal to the vector 1, 0, 0 dotted with 0, 1, 0, dotted with x, which is 1, 3, 1, divided by 1, 0, 0 dotted with 1, 0, 0 times the vector 1, 0, 0. I'm using this up here with my new two vectors, not my old two that weren't orthogonal, plus the vector 0, 1, 0 dotted with x, 1, 3, 1, divided by 0, 1, 0 dotted with 0, 1, 0, and that is times 0, 1, 0. And I believe if you do the calculations, this time you will get the vector 1, 3, 0. So 1, 3, 0 is the vector in the span of these two that's the closest to 1, 3, 1. And you could probably predict that would have been the answer to begin with, because you'll notice that the bottom coordinate has to be 0 in any linear combination of these two vectors. So 1, 3, 0 is the best you can do, getting close to 1, 3, 1. Graphically, if you want to depict what's going on in the picture, I have the vector 1, 3, 1, which comes 1 in the x-axis direction, 3 in the y direction, and 1 up. So this red vector is the vector depicted in the problem 1, 3, 1. And the answer that I got, 1, 3, 0, is the shadow of that vector in the xy plane. That shadow is also known as the projection. Okay, excellent.